Hi guys! This video is the second part of the two-part lecture on the topic related rates. We will be having two examples for today. Let's proceed to our first example. Water is pouring into an inverted cone at a rate of 8 cubic feet per minute. If the height of the cone is 12 feet and the radius of its base is 6 feet, how fast is the water level rising when the water is 4 feet deep? Clearly, this is a related rate problem because of the statement how fast, and that is, we wish to know the rate of the water level rising given that water is being poured at another rate of 8 cubic feet per minute. Now, to understand the problem, let us draw the diagram first. So we have an inverted cone container, which is always 12 feet in height and 6 feet in radius. Notice that the container is not changing. One of the first problems of this example is to understand that what is changing is not the container, but rather the water that is being poured into it. Now the water, of course, when you pour it, it will be outside. We cannot study the water outside, but what we can study is the water inside. Notice that if I have water being poured outside by the laws of conservation of mass, whatever is being poured from the outside to the inside, that rate will be exactly the same rate as how fast the volume of the water inside is also increasing. And because of that, I will let V to be the volume of the water inside the cone. Though note that the water is being poured into an inverted cone, the 8 cubic feet per minute actually will also be represented by the volume of the water inside. I also know that I'm going to be talking about volume primarily because of the unit cubic feet. As I have told you before, this unit here is a good indicator of what type of measure we are going to be studying. Now we also have water inside. Under the assumption that we are on Earth, then the water will follow the shape of its container, and that is, it will be an inverted cone. Now, we need more variables for our study, as is given by the tip. The rate given will be the 8, and we have a rate required. The rate required here is how fast the water level is rising. In that case, we want to know how fast the height of this cone is. Thus, I will let that to be h. And since we know that the volume of a cone will always be governed not only by the height, but also its radius, I will be letting it to be r. Notice that the variable r is not a rate given, nor it is connected to a required rate. But the rate can be acquired later on as it is important in the problem. Now let us now interpret each of our rates. Since water is being poured into, that means the water is increasing, decreasing, or remains constant. The answer for that is increasing. And that means dV over dt will be a positive 8. Our units will be cubic feet per minute. What we want is how fast the water level is rising, and that is dH over dt at the instant when h is equal to 4. So that means the 4 will come later on, as I have discussed before, that the instance usually is used at the last. Now you will see here that since the volume of a cone is 1/3 pi r squared h, it is very weird that we don't know the rate of change of r with respect to t. At this part, there are two possible solutions. The first one is you acquire the rate dr over dt. The other one is that instead of having a formula governed by r and h, I will find a way so that this will only be governed by h and not at all by r. In that way, I will have a relationship of v and h only, and thus dr over dt will not be used. whatever the solution will be correct. I will be using the latter one. That is, I will find a way to eliminate the r. And I will do that by noting that by similar triangles, r and h can be expressed by r over h equal to 6 over 12. And that will tell you that the r is just h over 2. Plugging it in our formula, I'll have a 1/3 pi r squared h. So I'll have now an h squared over 4 times h. Simplify that, I'll have a pi h cubed over 12. And this is a relationship solely between the volume V and our height h. We can now start to implicitly differentiate both sides. So I'll have dv over dt equal to pi over 4h squared times the derivative of dh over dt. As I have told you in the previous video, it is very important that the rates appear in your relationship. Otherwise, there is nothing to relate it. And then, we are now ready to get dh over dt, and that was just 4 over pi h squared dv over dt. Now, since we only need dh over dt at the instant when h is equal to 4, then by plugging in the value 4 at h, I'll have 4 times 8 over 16 pi, and that will be 2 over pi. And it just remains to conclude to say that since 2 over pi is a positive value, that the value of h, or the depth of the water, is rising at a rate of 2 pi. The unit feet per minute is obtained by the unit of h, and since the unit for the volume is a cubic feet, then the h here will be a unit of feet, and the time here is a unit for minute will be our unit for time, and thus we have a minute here. And that is for this example. The main difficulty in this example is the part where we need to realize that the thing that moves here is the water, and it should look like a cone. It is not stated in the problem, and thus it should be inferred. The next difficult part here is to relate r and h. For those of you who wish to find what dr over dt is, all you need to know is that if you implicitly differentiate both sides of this relation with respect to t, then dr over dt is equal to 1/2 dh over dt. And since dh over dt can be placed here, then I can just write exactly 1/2 dh over dt wherever dr over dt is being asked for. Now let's have our last example. A particle is moving along the curve y equal to square root of x. As the particle passes through the point 4, 2, its x coordinate increases at the rate of 3 centimeters per second. How fast is the distance from the particle to the origin changing at this instant? So we have a problem in the Cartesian plane, and I have a curve y equal to square root of x, and thus we draw it like this. Now to select the variables here, since the particle is moving along the curve, we can just talk about the rate it is moving by letting x to be exactly the x coordinate and the y to be the y coordinate. These are good variables, and it's not really because it's a point, but rather the x is the distance of, in this case, the x value here to 0, while the y is just the distance of the y value to 0. So this x and y are still lengths, instead of thinking of it as a point, though it will be talked about as a point in here, since this is the coordinate of the particle in the curve. Now, I will be interpreting now each rate as a derivative. I have a rate given here, and that's the rate for the x coordinate. But before that, we have how fast the distance from the particle of the origin is changing at this instant. So that means I need another variable here, and that's the variable from this point to this point. That's just the direct length of the line segment connecting the origin and our point xy. Now dx over dt will be at 4, 2 will be given by 3 centimeters per second. It is good to note here that unlike in the previous examples, the rate of change of x with respect to t is not constant for all time, for every point, but rather the value 3 centimeters per second is only valid when you are at the point 4, 2. At that instant when you are at 4, 2. And we also need to know what we want is exactly the rate of change of z at this point here. This type of example demonstrates that we don't really need to know what happens at every single point in time t, which makes sense. For example, if I have a car, it's almost impossible that the car will maintain a single rate for the whole expressway. So just like in this case, the x coordinate is changing at different rates at different points of the curve. But in our problem, being able to know the rate at a single point is already enough. It's just we need to write this properly later on. Now that we have identified what is being asked, we just need to relate our variables. Just like before, the relationship of z with respect to x is a distance, and it will be given by this distance formula, square root of x minus 0 squared plus y minus 0 squared, and that's just a square root of x squared plus y squared. Now, if you recall in optimization, instead of using the square root, you can remove it and just study the argument. That type of argument will only work for optimization, as we need to keep the square root here so that the rates that we have will be true and it will not have any discrepancies. So we cannot remove the square root. Though the main problem here really is that we have a dx over dt and we have a dz over dt, but we do not have a dy over dt, thus giving us two possibilities. Either we acquire dy over dt at 4, 2, or we remove it. The latter will be much easier since we already know that y is equal to square root of x. Then z will just be equal to square root of x squared and y squared will just be x, and thus giving us the relationship between x and z. And thus, implicitly differentiating this, we'll have dz over dt equal to 1 over 2 square root of x squared plus x times the derivative of x squared plus x will just be a 2x times the derivative of x dx over dt plus dx over dt. And since I need the value at the point 4, 2, I just plug in the values. I'll have 4 at x, and dx over dt at 4, 2 will just be equal to 3. So I'll have this quantity here, and that will be equal to 27 over 2 square root of 20. Since this is a positive number, then what we can say for sure is that the distance is increasing at this rate here, and I got the unit centimeter per second because the unit for the length of z is exactly the same unit that we have used for the length x, which is a centimeter, and same unit for time, which is seconds. And that's how you solve related rates. Now, I hope you enjoyed this video. Study hard and stay safe.